Okay, I'm back. Let's take this peak picked values. Let's just analyze the 35 isotope just for now. Let's go ahead and start a new sheet. Just so you can see I'm not cheating here. I've got all the stuff done down here, but I'm just going to go from scratch just like you will be in the lab. I'm going to select all of these peaks and come over here, and I'm going to paste them here. And so I've got my wave number value. I've got my isotope. And what I want to do is I want to make sure I have all of those significant figures. That's why we didn't type any of these numbers in. We want all of those decimal places because they're all measured. That's real experimental data here. And so we want to keep all of those values. We don't want to round our wave numbers. That would introduce error, be a terrible disaster for your uncertainties. Let's now assign the spectrum. So there's peak picking. We've picked the peaks. We've given the frequencies of every peak. That's peak picking. Now we need to assign them. Assigning them means we're putting quantum numbers on all of these transitions. So we need to assign the R values and the P values. And the J, J equals 0 to 1 or 1 to 2 or 2 to 3. That's what we're calling a spectral assignment. And so over here we're going to call it branch number, or branch. Let's go ahead and sort this by wave number value. So we're going to sort these. Let's do it this way. And we'll just sort that smallest to largest. Okay. So these should be our P branch lines. And in the middle would be the, we'll run out and it will go from P1 and then to R0 and it should go down. And these are our R branch lines. So the higher frequency ones are the R branch and the lower frequencies are the P branch. We need to find this middle point. We need to assign R0 and P1 first. So let's go back to our spectrum. I'm just going to grab this and copy it. And let's see if we can paste it over here on this sheet. Yeah, what do you know? So looking at this spectrum, our R branch is on the high wave number side. And so this is my R0 line. So the 2900, the one that's closest to 2900, is my R0 peak. So right here, 2906, okay, that's going to be R0. And then this one over here, if I hover over that, that is 2865. That's P1. And it's just that easy. All I have to do is assign those branch lines from the middle out. And so this next one is R1, R2, R3, etc. And you can just grab those guys, and you grab 3 of them, and Excel can figure out the trend. So we went up to R11. Now we've got P1, P2, P3. We can grab all 3 of those and drag them up. 4, 5, 6, 7, 8, 9, 10, 11. So we have up to P11. This is kind of nice. We have a symmetric number of peaks on either side. And so that's the spectral assignment. We've assigned every quantum transition. And now let's go ahead and, just for fun, let's put the J values on there. So we have J double prime and we have J prime, just for fun, okay? Just to exercise our skills in knowing what the quantum transitions are. So these are labeled by the J double primes. So this is 11 and it's a P branch, and so it's going down. So this then is 10. So it's going from 11 to 10. And so this one is then 10 going to 9. And this one is 9 going to 8, because these are P branch lines. So we have this. Let's go ahead and Excel can figure out the trend. 5, 4, 3, 2, 1. So 10, 9, 8, all the way down to 0. So those are our J values for these P branch lines. Now R is delta J plus 1. So this is going from 0 to 1. And this is going from 1 to 2, because it's an R branch. And this one's going from 2 to 3. And so we can drag these down. Excel figures out the trend if you grab 3 of them. And so here we have 1, 2, 3, all the way up. So it's the last one's going from 11 up to 12. So those are our quantum numbers. We've actually assigned quantum numbers to these spectral peaks. It's pretty cool. Now, we could do a regression analysis to get our B values and all of those terms that we have in that lab handout and in the lecture. Let me go ahead and pull that lecture up so we can get the regression analysis equation. Okay. Okay, so I'm going to go ahead and clip that equation out of the lab. I'm going to snip it and paste it into Excel. And so we've got this guy here. And so I'm going to paste this in here. This is our little regression analysis equation. And it tells us to use M. And so we're going to create an M quantum number here so that we can do a regression analysis for both the P and the R branch together. Okay. And so for the P branch, M is just equal to minus J double prime. So this is equal to minus J double prime. Okay, so that's minus 11. And that goes all the way, and that only applies to the P branch. And so it goes down and stops. And then for the R branch, it's equal to J double prime plus 1. And so it starts at 1 and goes all the way up. And so that's the M fake or running quantum number. Now we could do a regression analysis related to M, but what we want to do is use this particular equation. If we have 3 columns here, and we have 2M and this piece here and this piece here, then the coefficients of each of those columns will be nu 0, BE, A, alpha E, and DE. So we're just going to follow this instruction here and create those columns. And so this is going to be the 2M column. So that's equal to 2 times M. All right, copy that down by double-clicking the little square. Then this is going to be the minus 2M minus M squared. And that's close enough. Okay, we understand what's going on. And that is going to be equal to minus 2 times M minus M raised to the second power. Okay. And then double click that little square and it copies that down. Our third column is going to be the minus M cubed. Minus 4M cubed. That's enough to know what we're doing. Oh, it thinks it's a formula. Okay, when we want to do this, we can put an apostrophe in front, and that tells the Excel that it's text. Minus 4M cubed, and then it'll accept it as text. Okay. All right, so then we say equals minus 4 times M raised to the third power. And notice how that's a huge number for the high quantum numbers and almost nothing down here. So there's our 3 columns. Okay. And so what we want to do is these are the independent variables, and we're going to create the dependent variable as the wave number value. Okay. Because this formula here will take these 3 columns, and this third column times the dissociation energy plus the second column times the vibration rotation coupling constant plus this first column times the rotational constant plus the vibrational frequency will give us our transition frequencies. So these here are the Y values of this regression, or the dependent variables. These columns are the independent variables, or the X values. So we come up here to the data ribbon, and we go to this data analysis toolbox over here. We click on that, and we scroll down until we find regression. Now, if you don't have this data analysis toolbox, let's go ahead and cover that, because you may not have it turned on in your Excel. You come over here to File, Options, and then down here it has Add-ins. Oh, you don't see that dialog box on the video. Let's see. Let me change something new. Let's see. Generic overlay. Yeah, so let me add a display capture. Okay, that's fine. Display capture, we're going to put that underneath the video overlay. Okay, and underneath the overlay, generic overlay, yep, that'll work. And then when we go back to here, we can see it. Okay, so I went up to File Options, and I got this dialog box. And then over here under Add-ins, you click Add-ins, and you can come down here at the bottom. Let's see. And you click this Manage Add-ins, Excel Add-ins, and you hit Go. And when you hit Go, you have this option of checking the Analysis Tool Pack. If you click that, then you get the Data Analysis Tools up here. And if you click Solver, you also get Solver. And we're going to need Solver later, so go ahead and click that and make sure you have it. So there we go. Let me go back and undo the display capture because it'll make it a little better just to have Excel on here. Okay. So I'm going to click the Data Analysis, and I'm going to scroll down and hit Regression. And regression is just a complicated least squares fit, okay? It'll do it for multiple columns. Normally you do least squares fit. Back in high school you did it by hand for one column of data. Regression analysis is the same thing, but you can do for multiple columns of data. So the Y range is the independent variables. Okay, so I need to turn on the display capture because it's not showing. Okay, so I hit the data analysis, scroll down and click regression, hit OK, and then the Y variables here are going to be my frequencies. So I'm going to select my frequencies for the Y variables. And the input X range is going to be my 3 columns of data. Okay. And actually, if I want to select the column headings, let's go ahead and do that. So I'm going to select these guys. I'm going to collect that wave number value 2, so the title and the numbers, and then I'm going to select this one with the titles 2. Okay. And I'm going to say these have labels. And then I'm going to pick a new worksheet, and I'm going to call this H35CL regression. Okay. And I'm going to hit OK. And what we see here, we get, so this is a nice little trick. What I do is I will capture, let's see. I will select everything and double click between 2 columns, and it auto scales everything. And then I'll click somewhere else. So we have this intercept, the 2m column coefficient, this one and this one. So what do these mean? Well, let me go ahead and go back and get our equation here. So this guy right here, copy and paste. And so we have is the coefficient of the 2m column is BE. So I can come over here and I can say this is BE. And the coefficient of this column is alpha E. And this is DE. And the intercept is nu 0, the vibrational frequency. So those are my values that I have in that spectrum. Now what's amazing about this is that it doesn't just give you these values. The reason we want to do a regression analysis is we get the standard errors. These are the uncertainties that we have in these values. And they're quite good. We know the vibrational frequency now for HCl is 2,885 wave numbers, and our uncertainty is 0.05 wave numbers. So we're certain to the hundredths place on that frequency. So another way to think about it is our significant figures are all the certain digits plus the one uncertain digit, and our uncertain digit is in the hundredths place. So we have 1, 2, 3, 4, 5, 6 significant figures in our vibrational frequency. Our rotational constant is 10.5907 and all those things, and here's our uncertainty, 0.005 wave numbers. So that's also very good. We have 5 significant figures in our rotational constant. Our alpha E, that vibration rotation coupling constant, is 0.3026 plus or minus 0.0007. And then here's our dissociation energy, and it's 0.0005, and then this is in the next digit over. So we have 2 significant figures on our DE. We have 4 significant figures on alpha E. We have 5 significant figures on BE and 6 significant figures on our vibrational frequency. Now, the p-value bears some comment here. This is the probability that random noise gave the values in column A. Okay, and they're quite low. Okay, if it was 0.05 p-value, that would be like a 95% confidence in the values in column A. So we have like a 99.999999 times 89's confidence in that vibrational frequency. So that's pretty amazing. These are extremely low p-values, which means that these values are statistically significant. Okay. If this value is above 0.05, then we say it's not statistically significant. Okay. So the p-values are what you want to look at along with your standard error. If we wanted to calculate the RSD for each of these, so RSD, let's do this. Let's calculate it in this column, RSD, and we'll take all of these guys here and copy this down here. And so the RSD is equal to the uncertainty divided by the value itself. And so these are our RSDs. They're all really low. Our coefficient of variation, the CV, is equal to the RSD times 100%. And so you can just, Excel will do a percent. You can just make these guys percentage data format. So come up here and hit percent. And it's essentially 0 because it's rounding. Okay, so those are our percent errors, our percent uncertainties, the CV values. So 0.002% is our uncertainty in the vibrational frequency. But for the dissociation energy, not very well. We're 5.6% uncertain about it. That's still pretty darn good. So we wouldn't keep more than 2 digits of uncertainty. So we would report these like 0.25%, 0.051%. So those are our CVs for our various values that we've determined for HCl. And that's why we want to do a regression analysis. It studies all of those peaks, it calculates all of those B values, and it gives you an average and a standard deviation. And that's what we have right here, our 10.59 wave numbers plus or minus 0.005. Now, if we wanted to do a 95% confidence value, then our so we're going to calculate our confidence intervals. Okay, and we'll do it for all 4 of these. Copy, paste those down. And so what we're going to do is we're going to say Z95 is equal to 1.96. Okay, And we can explain that. I'll explain the statistical analysis later, but our 95% confidence interval is going to take our standard deviation times 1.96. And so we have our middle value and our Gaussian distribution, and we want to capture 95% of the area under that curve. And if we go from the center to the left, 1.96 times sigma, and to the right, 1.96 times sigma, then the area under that curve, it captures 95% of the uncertainty surrounding our values. And so we're going to say this is equal to our value up here minus this, and I'm going to anchor that one, times our standard error. Okay, and I'm going to just drag that down. And so this is our lower limits. Okay, I'm going to drag this guy over and fix all of the mistakes. So we're going to drag this back over here. And I'm going to change that minus sign to a plus sign. And so these are our upper limits. So we're 95% sure that our our rotational constant is between these two limits. So that would be a 95% confidence interval. You could also say that it's you could say that this is equal to 1.96 times our standard error. And so you could write, you could say a reported value. And now look at this. This is going to be a fun formula because it's going to combine text and the numbers. And so we're going to say that this is equal to our new zero. Okay. And we're going to say that we're going to round that to 2 decimal places. So we'll say round this number to 2 decimal places. Okay. And then we're going to put an ampersand there, and we're going to put a quote which opens text, and we're going to space alt 10177 gives us a plus minus, space, quote, ampersand, round this value to 2 places, and we're going to hit enter. And isn't that cool? We've got our reported value of our 95% confidence interval for a new zero is 2,885 wave numbers plus or minus 0.09 wave numbers. We can copy these down and get all of our values here. So this is our rotational constant, 10.59, plus or minus 0.01. We need to change our rounding on this one, so we're going to round it to three decimal places. No, let's see. Yeah, we'll say 3. 3 and 3 because they're smaller values. And this one we're going to round to 5 decimal places. Yeah. So these are our 95% confidence interval round reported values from this regression analysis. Okay, now we can watch a separate video on the propagation of uncertainty because we want to take this value, this new zero value, and we want to compute the force constant and propagate the uncertainty. It's not proportional because it's a square root dependence, and so you have to take into account that square root dependence. And then the same thing here, from the BE value, we're going to compute the bond length and propagate uncertainty. Because it also is a square root dependence, so you have to take into account the change in uncertainty because it's not linear. It's a square root dependence. And so these would be derived values, the force constant and the bond length. But you have to then take your uncertainties from these standard error columns and propagate them into what's the uncertainty in the bond length, if I know the uncertainty in the rotational constant. And what's the uncertainty in the force constant, if I know the uncertainty in the vibrational frequency. Okay, so that's the next piece of the analysis. Hope this video was helpful.